Good morning, everyone. I want to officially welcome you to today's webinar, Plant Growth Regulator Effects on Winter Stress Tolerance of Annual Bluegrass Putting Greens, presented by IntelliGrow and taught by Emily Meriwitz, PhD. My name is Lisa Wick. I'm the Senior Manager of E-Learning Programs here at GCSAA and today's moderator. We are recording today's event, and you'll get access to that recording via follow-up email. Your audio is muted. But if you have questions, you can either type them in the question answer box, or there's a raise hand button on the GoToWebinar control panel, and you can click that and we can unmute your telephone or microphone at an appropriate time and you can ask the question directly. Today's session has been approved for 0.1 GCSA education points. At the end of the program, we'll give you a code that you can use in the education affidavit on the GCSA website. We hope you find today's webcast valuable. It is brought to us in partnership with IntelliGrow. IntelliGrow is dedicated to transforming plant protection for more resourceful growth. Partnering with leading researchers and industry professionals, they challenge conventional wisdom to create smarter growth for a better world. Drawing on over 20 years of experience in agriculture and over 6 in the professional golf, turf, lawn, and landscape industries, IntelliGrow offers innovative solutions, including Civitas Turf Defense, to help customers achieve top quality results. Today's webinar is taught by Emily Meriwitz, PhD, an assistant professor in the Department of Plant, Soil, and Microbial Sciences at Michigan State University. She earned 2 bachelor's degrees and her PhD at Rutgers University. Plant physiology, turfgrass and crop physiology, abiotic and biotic stress, and plant hormones are her general areas of expertise. Meriwitz teaches 2 courses at MSU and has published a number of turfgrass research articles. Please join me in welcoming today's presenter, and I'll turn it over to Emily.
Well, thank you, Lisa, and thank you to all the attendees for attending this webinar this morning. As Lisa said, if throughout the presentation, you don't have to wait till the end. If you have any questions, feel free to let us know, and we will try to answer all the questions as we can. So, as Lisa said, I'm going to be presenting on essentially winter kill stresses of annual bluegrass putting greens, and keep in the back of your mind that this research hopes to kind of expand beyond just annual bluegrass putting greens, and that it can apply to fairways and other turf grasses as well. I'll kind of start off saying, of course, why ice is important and why it's a problem, and kind of give you some insight into, what we were thinking before we started doing this research, and why we started to do this research in Michigan. So if we go ahead, so our research center is located in East Lansing, Michigan, and in the spring, so the winter of 2013 to the spring of 2014, this is our farm. These pictures are our farm, and we have a pretty significant acreage of putting green, of either creeping bluegrass or annual bluegrass, of a variety of different cultivars, and we have some higher cut grasses as well, athletic field type situation. But generally, we saw a whole lot of ice damage, primarily on our putting green surfaces. And there you can see, some of the variation in there, which I'll get to the cause of that in a little bit. But this spring and winter, especially, was highly damaging in Michigan. And so we, even just from our farm, we knew that this ice was a huge issue. And so almost this entire area in the picture was completely covered in ice. We had a huge ice storm right before Christmas, and so people were out of power and had major issues during the holiday season, which was very unfortunate. And then as we kind of thawed out in the spring, we found how much damage had happened to golf courses, and it was a major issue. So kind of when it started to warm up and we kind of started to see so much damage throughout the state and in other states as well, we knew we needed to do something. This was an emergency situation in Michigan and in other states. So we, along with my colleague Kevin Frank, we conducted a survey just to see could we just get a quick answer? Okay, was there something that everybody was doing that was causing this damage, like something in common that everybody was doing, or were there certain management practices that where people saw less damage, or certain management practices where people saw more damage? We're kind of trying to ask a bunch of questions and get some answers in terms of, okay, where should we dig into this problem? Where should we start as researchers? And there's been ice research going on at Michigan State University back to when James Beard was here back in the 60s or something. But certainly, we have new products, and we have new management strategies now that are highly different than they were back in the 60s. So, and not all the questions were answered back then. So we certainly need to, kind of revisit ice research and kind of make it a priority again. So we did the survey, and we had, a good number of respondents from Michigan and some surrounding states and areas as well. And go ahead. So as I said, we asked, a bunch of questions to try to see, how extensive the ice damage was, and, were there certain things that people were doing or not doing that kind of were associated with more or less ice damage. So, just to get an idea of the damage people had, we looked at, we asked, did your greens experience any winter kill this year? And it was, overwhelming majority that said, yes, we had, a pretty good amount of ice damage. 38% of people surveyed, and of course not everybody answers these surveys, but 38% had damage to 9 or more greens. And if you're members of the audience or are, a superintendent of a golf course, or a related field, or related turf manager, then you know how much money this can be to renovate this many greens, and how significant that's going to damage your income if you have to delay opening in the spring. And this season, as an example, was already delayed because it was such a cold, terrible season. So so 38,000 square foot of green was like the average amount of damage that people saw, and it ranged from like only 20 square feet to 95,000 square feet. So pretty big range of damage people were seeing. And we went out. We weren't just relying on this survey as our only source of information. We went out, and like all the turf professors, and actually the dean of the College of Agriculture, the dean of our College of Agriculture and Natural Resources, we went out and we met with a bunch of superintendents, and we saw firsthand the damage that was happening, or that had happened on golf courses. And so we talked to the superintendents also to see what kind of management they were doing or not doing that could be associated with this ice damage that they were experiencing. So some more questions. So how many days were your green under ice? And so it's almost devastating numbers here that greater than about 66% of the people had greater than 40 days of ice, and that ice was generally pretty deep, 1 to 3 inches in depth. So again, pretty big majority of people that had damage to their greens and had significant duration of that ice on their greens. So the issues so it's important to kind of step back and say, okay, so how can this ice happen, and why is this damage happening to the golf courses or putting greens, and also that the reason why you as superintendents, or you as members of the golf course industry or turf management industry may not have great answers to any winter problem is that it's really hard to do research on this stuff. First of all, the thing that comes to my mind is you can't send somebody out to do research on this field, A, because it's completely covered in ice or snow, not accessible, and B, because it's just not nice to do that to somebody. It's probably at some days we had -20 temperatures. So the reason why heat, there's a lot more research on heat stress and things in the summer is obviously because it's kind of almost easier to do research on, but also because the ice accumulation can be highly variable. So not only from year to year, you're never sure if you're going to get it or not, So in research, we always have to repeat experiments from year to year, so we don't know if we're going to always get ice or not, and that makes it hard and more expensive if you have to extend it to 3-4 years. And there's also a lot of variability, in how ice can accumulate. It can form in different ways. We had a lot of damage that season that I discussed because we had just an ice storm, so it was just instant ice accumulation, and then the temperature stayed so low throughout the winter and spring that the ice just persisted. But there's other ways that ice can form. So melting of snow, if you have kind of a winter that fluctuates a bit more, that causes snow melt, that causes ice to accumulate on the green. And then there's the variation of the type of ice that it is, whether it's porous or impermeable, and then whether and of course the duration is another variable. And then so the damage, so it's not easy to pinpoint, okay, this ice is causing X damage to this grass because of this reason. There's a lot of factors that can go into ice damage and winter kill in general. Generally, there's been some research, as I said, since the 60s on this, and so we know that ice, especially if it's impermeable, can really reduce the oxygen available to the plant, and oxygen is important for respiration, which is the conversion of carbohydrates into a source of energy for the plant to use to grow and create roots or maintain its roots, that kind of thing. So oxygen depletion is a big factor here. And also there's a buildup of other gases from as I said, respiration going on in the plant or in the soil from all the microbial activity, and that can create sort of kind of byproducts of respiration and other metabolic pathways that certain microbes have, can cause ethyl butyrate to form, methane, and other harmful gases. And ethyl butyrate really can penetrate plant cell walls and kind of cause holes and do all kinds of damage. So, and as we know, the crown is the most important overwintering structure for, at least for most putting green species. For other species, it can be rhizomes and things like that. But for the purposes of our putting greens, generally we want to see those crowns survive into the winter. So I think we'll move on to the next slide. And so I talked a lot about how variable this winter these winter issues can be, but also we get the variation because of the cultivars that we use, or the ecotypes or the species that are highly used on putting greens. The creeping bentgrass, we would all love to have 100% creeping bentgrass, and maybe you do, that's great. But not every area of the country, especially in Michigan, is able to kind of keep 100% creeping bentgrass. It's known that most people have generally a mix of annual bluegrass and creeping bentgrass, or just annual bluegrass putting greens. But with ecotype variation in annual bluegrass, you can have one putting green that's completely different than the putting green on your next hole. And so from my perspective in research, it's hard to help turf managers in that situation, because the research that I do maybe on one ecotype might not translate until to the next ecotype. So but generally, so that's why I'm trying to find chemical application type of strategies, or things that might help all ecotypes, or that might help improve annual bluegrass performance of the winter issues in general, and hopefully not just ice, but just generally increasing low temperature survival, and all the damage that these grasses might experience in the winter time. So so going back to the differences, so creeping bentgrass can generally survive around 120 days of ice, whereas annual bluegrass has been shown to only survive like 45 to maybe 90 days of ice, but 90 I don't think I've ever seen 90. So as we said, management practices have changed. This was from the 1960s, so management practices have changed since then, and it seems like maybe the management practices now have reduced the amount of survival of annual bluegrass in the wintertime. So here just a picture of one putting green in our research station that you can have. See, as I said, you have Poa annua right next to another Poa annua, and one is okay and one is dead. And it's hard to say. Perhaps this could be a difference in the type of ice that was here, or the duration of the ice, or it could be ecotype. And I think this was ecotype variation here. But then you have a creeping bentgrass on that same putting green that did just fine and survived. So, kind of a lot of complication here, which is why, it's not an easy answer to just get, XYZ management practice that's always going to prevent damage. So, but, there are a lot of different management practices that can be done to reduce ice damage. Some, are feasible in terms of your budget or, labor that you have, and some may not be. And so again, that's why we're interested in this plant growth regulator type of research that, could be budget friendly for everybody. And, it might already be a management practice that you're doing in the fall or, in the summer or in the spring. So it wouldn't be too much more to just make a couple applications of our recommended treatments before the winter. So just to go through them, top dressing, of course, you can add like a layer of sand or a layer of maybe black sand to reduce the amount of, or increase the amount of irradiance or warmth of the green and prevent ice directly. Cutting heights is actually something we're hoping to do some more work on, because it seems like it hasn't been researched for many, 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 many years. Hopefully in the future we'll kind of have a better answer on cutting heights regarding annual bluegrass, so maybe stay tuned for a future GCSA seminar from me on that. Tree removal, of course, would allow the sunlight to keep the green warmer and maybe reduce, and also help the plant before going into winter in terms of carbohydrate accumulation. Snow removal, getting, if it's feasible in terms of labor, and if you are able to do it without causing damage to your green, that would of course reduce any melt that could occur that could cause ice. Drainage, whatever you can do to get that water to move off your green or go through your green is going to help reduce ice. And covers, either permeable or impermeable. And so we did some, within that survey that I was discussing, we did some questions related to these management practices to see, okay, was everybody covering, was nobody covering, and did they see ice, did they not see ice, that kind of thing. So I have a few more questions like that. And I didn't put all the questions that we asked on here, but just so you have an idea. So we asked, did you use covers? Overwhelming no response, which I guess I was surprised. But it can be expensive to do. So but the people that did, 88% used the permeable cover and 12% used impermeable, which was only one person. And then, so as I said, we asked a lot of different questions like this. But one of the things that I was most interested in was, did you use plant growth regulators? And we're trying to see, which ones they might have used or not used. So we got yes for plant growth regulators from not the majority, and most of the people said no. And the people that did use PGRs primarily used Primo or Trinexapac ethyl, and so that gave me some indication. But as I said, when we went out and walked some of these courses and talked to the superintendents, we kept hearing certain treatments that were done, and we kept hearing Civitas actually. So and there was this one course in particular that they had, I guess, a 9-hole direction that you could go, so a different set of greens, and then an 18-hole direction. And they had not treated their 9-hole direction with Civitas, but they had treated their 18-hole direction with Civitas. And so the 18-hole area their putting greens did much better. And though they weren't sure whether it was just, environment, because the 9-hole area was lower and there were some, environmental differences, but, that Civitas kind of stuck in our mind. So when we, I'll go back. when we sat down as a faculty, we all met and kind of put our heads together and said, what are we all hearing? What do we want to do to help with this, emergency winter situation that we were having? People wanted answers, as I'm sure, those you guys in the audience want answers to, what's the best way to prevent my greens or whatever turf area in the winter. So we put our heads together to try to, come up with the best answers we could. And so we came up with a list of treatments that we have for this study that I'll talk about in a minute. So, but generally, we just wanted to know whether there are simple chemical treatment strategies that can promote annual bluegrass tolerance of winter or ice-related stresses. And so I kind of lumped the Civitas that I mentioned in with plant growth regulators. It can do some changes to plant hormones in terms of systemic or induced defense responses. I think they're calling it a plant protectant, but generally I'm just going to kind of abbreviate them all in my speech with just plant growth regulators. And so we, and I really wanted to compare, compare that plant protectant to some of the plant growth regulators that we heard, from the survey and that we know people, use heavily. So that was trinexapac ethyl, which inhibits, or Primo, which inhibits gibberellic acid activity, and so reduces essentially stem or leaf elongation. And we wanted to see, compared to some of the other classes of PGRs, how do the other PGRs, compare to trinexapac ethyl, and how do they compare, obviously, to no treatment. So we also use paclobutrazol, and we use methfluidide. And so paclobutrazol, can inhibit kind of earlier in the pathway in class A, or trinexapac ethyl kind of inhibits later in the gibberellic acid pathway, and methfluidide is affecting cell division, kind of a different pathway than gibberellic acid. So, and my other goals with this research was to find something that, some type of management strategy that you could do that would kind of prepare you for the worst situation, but wouldn't change how your turf looked in the fall, or wouldn't really change, or maybe would improve how your turf looked in the fall or looked in the spring after winter. And, perhaps, covering or something like that is preparing for the worst, but those, especially impermeable covers, could maybe do some damage too, because it's kind of acting like ice, right? It's kind of covering and preventing oxygen exchange and that kind of thing. So, that type of covering preparation could cause, and it could, be a factor in the spring. If you get fluctuating warming and cooling temperatures, those covers are going to overheat. So when do you remove it? When do you take it off? That's always a question. So this chemical strategies, hopefully wouldn't cause much change, or, would improve, what you see, your turf performance in the fall and the spring. So that was, a huge goal for me, and so, of course, still is in my research. So I could probably spend an hour just talking about, what the plant is doing going into winter. And the term for that is acclimation. How are plants, getting ready to go into the winter? What are they doing to protect themselves? And, what happens in the spring when they're kind of coming out of winter or deacclimating and going into getting ready to start growing and greening up. So I guess probably spent a long time on that, but we had to just pick some things, right? We had to just pick some measurements to see, okay, are these plant growth regulators that we want to look at, are they, seeming to protect the plant in certain physiological ways? So we, so a major one that is looked at for any type of cold research or ice winter research would be fatty acids. And so fatty acids are primarily a component of cellular membranes. Remember back from plant physiology, cellular membranes are composed of lipid bilayers, and they have a phosphohead, and then they have fatty acid tails. Well, those fatty acid tails within the cell membrane can shift. They can, the plant can change them in order to, survive winter. change them when it comes into warmer temperatures. And I'll explain that a little bit later. But there's also a shifting of water around in the plant. The plant doesn't want ice to form inside of its tissues, so it generally tries to kind of dehydrate itself before experiencing any low temperature conditions that might cause freezing inside the plant. So there's this shifting of water, there's this shifting of carbohydrates. Generally carbohydrates are attempted to be stored in the crown tissue for future growth coming out of the winter. And there's also, an alteration of stress protection type responses, like maybe shifting antioxidants or other things going on in the plant. So for the purposes of our research, I first wanted to, and mostly because, how fatty acids are responding in annual bluegrass is not well known to begin with. So even if our treatments didn't do anything, I still wanted to know how these fatty acids are responding in annual bluegrass going into winter and coming out of winter. So so as I said, the plant during acclimation or during the time period in the fall where it's getting ready to overwinter, the fatty acids, the plant can manipulate its fatty acids, and this is kind of a general process over time. And I'll try to explain this the best I can. If anybody has any questions, please stop me here. But generally, saturated fatty acids are like butter, okay? So butter, we know, is kind of the unhealthier thing for us if you compare it to something like olive oil. So butter has more saturated fatty acids in it than olive oil. So at room temperature, saturated fatty acids are a solid, right? If you leave a stick of butter on your counter, it gets softer, but it'll generally, kind of stay in a kind of rigid state. Whereas olive oil, if you leave it on your counter, it'll stay a liquid, okay? So if you think about that under low temperatures or high temperatures, the plant can kind of switch between butter or an olive oil type of fatty acid composition. So how the membranes are gonna, kind of protect the rest of the stuff in the cells by shifting whether they have more or less saturated or unsaturated fatty acids. So in the wintertime, where things become very rigid, the plant would prefer that cellular membrane to be more fluid. So as less rigid as it can get it to be, more of in a natural state is how the plants are able to better survive low temperature conditions. So the plant's ability to kind of maintain unsaturated fatty acids or convert to unsaturated fatty acids are associated with cold tolerance. Okay, so hopefully that made sense. So our hypothesis, for this study, as I said, is that, we're hoping to see whether, or we thought that there are certain PGRs or other chemical treatments that could alter turf growth habits and therefore affect the turf grass survival, or particularly the crown membrane survival and fatty acids within those crown membranes under winter stresses. So we had several objectives, and I mentioned a few of them already. So as I said, we wanted to make sure that these treatments were not going to, negatively affect turf performance in the fall when they were being put down, or in the spring. So we evaluated the field both before and after the winter, and we evaluated whether PGRs would reduce annual bluegrass necrosis under ice or non-ice in kind of controlled low temperature conditions. And then we wanted to determine some of the physiological mechanisms associated with PGRs and how they're affecting winter kill stress. So I've been talking a lot about our treatments, but I never showed them to you yet, so here they are. So we had 5 treatments. One was our control, or no defense, and these are all labeled recommended rates. We didn't want to really mess with that yet at all. Of course, the companies know more about these chemicals than we do, so we went with the label recommendation. And then so we also had methfluidide, propiconazole, and trinexapac ethyl as well. And their application frequency is down here. They were made every 2 weeks throughout the summer into early fall. And for 2014 and 2015, we had pretty similar dates. We had July 31st to October 9th, and then August 5th to October 14th for our applications. And so all these treatments were put out into the field, as I said, so, you know, kind of get to replicate what a turf manager would do under, you know, normal conditions at his own golf course, or her own golf course. And then, but we also did this because we wanted to get that natural acclimation to happen in the field. We didn't want to have to try to, you know, replicate what happens out in the natural world in some type of growth chamber in terms of, you know, slowly decreasing the temperatures, because it's just easier to do it out in the field, and it's more, you know, realistic to have it happen out in the field. So as you can see, all these plugs. So once we had natural, so after we were kind of done our treatments in the field, and we, you know, looked like from the turf, visually we saw that, you know, we had acclimation kind of happening when we started to take plugs. And these plugs we, let me have a picture. We brought into a low temperature growth chamber, which can hold, you know, pretty low temperatures, even with the lights on, and has ample space for us to, you know, grow a lot of different plants. So that's where we were able to control the environment. And then, so, you know, it's kind of listed out here. And the light levels we tried to replicate, you know, we went out on a couple of cloudy, you know, it's always cloudy here in Michigan in the winter. We went out on a normal day in the winter, and we, you know, measured the light levels on a few days, and we took the average of that, and we got, you know, the average light level that we saw. So that's what we set the growth chamber to be, the light level in the growth chamber. And then so we had, you know, a large amount of plugs so that we were able to kind of destructively sample or just take out of the low temperature growth chamber these plant plugs at given time periods to represent, you know, 0 days of ice, 20 days of ice, 40 days of ice, and then 60 days of ice. And then we had plants that were covered in ice or not covered in ice. And then we would split those samples and use them for either a regrowth assay in the greenhouse, or we would use them for that fatty acid analysis that I talked about. And then so we let them recover for about 21 days in the greenhouse, and we had 4 replicates of each of these samples in each of these chemical treatments. So here is a picture of the plants in the low temperature growth chamber, some without ice and some with ice. And not to bore you too much with the experimental details, but essentially we're able to do statistics, you know, following our experiment. And so, as I mentioned, we measured things in the field to evaluate whether, you know, the turf performance or turf quality was up to par with, you know, with what we wanted. And when we also measured spring green up, and then from the controlled experiments, we measured fatty acid ratios and percent regrowth from that splitting of the plugs, as I mentioned. Okay, so here's the fields in late summer. So the treatments have already been going on, and you can already see some, you know, treatment differences within the plots. And here in late fall, again, you can see some of the plots. I probably should have labeled them here for you, but some of the plots, you know, looking different than others. And so we took plugs from each of these plots and then evaluated them. Okay, so here's our field results, and this is to orient you a little bit. The date is on the x-axis, and then visual turf quality is on the y-axis. So, you know, this was essentially looking in the fall at, you know, whether we had any treatment differences and whether this would be a negative or a positive. With these winter protection treatments that we wanted to try were, you know, kind of a negative or a positive for fall conditions. And so if you look first at the untreated plants, which is the darkest gray end bar here, it generally kind of hung out in the middle. And the plant growth regulators, methfluidide, propiconazole, and tranexapac ethyl, at least on September 15th, it wasn't really different than the untreated. So no real negative effects going on here. Civitas was higher, statistically high, or not statistically higher than the untreated, but was statistically higher than the other plant growth regulators. So if there's a different letter, then they're different. If there's the same letter, then they're the same. So later in the fall, we did see some changes in turf quality, but it wasn't consistent in both years. So we can't say that any of these treatments were worse than the control, because we certainly did not see that the following year. And this could have been, due to slight differences in, the weather or environmental parameters, or, the precipitation between years or something like that. Or we certainly got more differences the first year than we did the second year. So Civitas seemed to kind of overall, at least in the first year, it'd be higher later in the fall, but that was not significant in the second year of the study. So what I conclude from this is that, these treatments don't seem to be, really negatively affecting the turf consistently, and they certainly weren't, there wasn't any, major improvement, but there was some slight improvement with Civitas at least one of the years. Okay, and then if we switch past the winter and go into the spring, just to stick with the field results, we looked at spring regrowth, or essentially, the rate of spring green up, and we saw that. We again focusing on our untreated compared to everything else. Got a lot of A's going on here, right? And the untreated is A. So really not a major improvement in spring green up in either year. So it really is not changing too much. There is some slight reduction due to treatment with methfluidide. But earlier in the spring, and then it seemed to kind of catch up later in the spring. So I wouldn't say that these treatments, had a major effect on spring regrowth. And that's, important to see, because these are plant growth regulators, right? They're regulating the growth. So they certainly could have lasting effects from fall to spring that, could, reduce or increase the growth rate that we saw. So, kind of neutral on the results that we saw. We were kind of happy that it wasn't these major differences that we saw. And so now it's just important to look at, what did it do to the ice survival or the low temperature survival. So that's what I'm showing here. So I remember back to my growth chamber picture, I showed ice or no ice, and then I said we split them in half. So you'll see kind of like a half of a plug in these pots here. So these pictures are in the greenhouse after 21 days of recovery. And these pictures were samples that were taken after 20 days under ice in the low temperature chamber. And so, untreated, maybe two little guys coming out, two little tillers coming out there, whereas Civitas and propiconazole, methfluidide, for example, had maybe significantly more regrowth that was occurring in these plugs. So, just visually from the pictures, we could see that, Civitas definitely was improving the recovery after ice in the chamber. And we're actually, surprised that only 20 days of ice, which doesn't always, kill annual bluegrass, we saw these major differences. And, our low temperature chamber conditions are very extreme. And it's a very extreme stress, because, this entire pot is frozen, whereas in the field, the soil would stay thawed. And so the fact that we're using this really extreme stress and you can get this difference in survival is actually really impressive.
Before you go on, Emily, I have a quick question for you.
Sure.
Would those conditions in the greenhouse be more like the impermeable ice sheets?
In the green, so the greenhouse is, oh, you mean in the low temperature growth chamber?
Right, yeah.
Right, yeah. Yes, it was impermeable ice, and we frequently misted it to maintain that ice layer. And I don't think I mentioned it, but there was like we created an inch of ice on top of the plants. So yes, it was more like an impermeable. Yep.
Okay, thank you.
Sure. So if we quantify that and kind of put that in graphical form, so we can, for each year, look at the plugs that we took out that were either non-ice covered or ice covered from that low temperature growth chamber at 20 days, 40 days, and 60 days. And so, each of these were had the same amount of time to recover in the greenhouse, but they experienced 20 days of ice, 40 days of ice, and 60 days of ice. So if you look at, obviously, percent regrowth, the higher regrowth, the better. And so if you look at, let's see, blue is Civitas, and then our other growth regulators, and then the teal color is the untreated. So, pretty big differences in terms of the amount of survival that we got between the treatments. Civitas, overall always was significantly higher than the untreated plants and significantly higher than trinexapac ethyl. And methfluidide and propiconazole were sometimes more significant than the untreated. Trinexapac ethyl looks like it's lower, but it's not significantly different. So we can't say that treatment with chemo reduced or had any negative effect on these plants. They were the same as the control. So that was 2014. That was non-ice covered. And so if we look at the same data for 2015, we got less significance this year on the first 2 days, but on the last day, we did see that methfluidide and propiconazole were higher than the untreated. Civitas in this year for no ice cover wasn't significantly different, but we'll see that under the ice cover that it did come out significantly different for both years. And this can be due to the fact that the difference in years for any of this data could be due to the fact that we had differences in acclimation, right? We let them acclimate naturally in the field, and any differences in that year could result in differences in how these plants are able to survive. So we're not surprised that the years are different. We generally see the years be different when we do field research. So that kind of explains that. And then so this is just 20 days after no ice covered plants, and so the plants that weren't severely treated with ice or temperature, obviously were still healthy. They're able to just kind of reassures us that what we're doing is right. And so this is 2014 regrowth of the ice covered annual bluegrass. And so as I said, you saw big differences in these ice covered plants due to chemical treatment compared to ones treated with either TE or untreated. And that was consistent for all the dates. 2014 and 2015 wasn't significant for 20 days, but they were significant. Civitas at least was significant for the 40 and 60 days compared to the untreated. Okay. So again, just so 2015 for just 20 days under ice cover, we didn't see too much damage, which we expected because 20 days is not generally lethal for annual bluegrass. So it's kind of just checking that, again, what we're doing seems to be realistic. Well, when we took them out after 40 days under ice, we could see that difference. We saw, so this is trinexapac ethyl, had less growth. Civitas turf defense had, pretty good percentage of regrowth happening. In the untreated control, looked more like kind of in between trinexapac ethyl and Civitas in terms of how much regrowth was happening. Same for 60 days under ice, we had very similar response. So, it seems to be consistent for the, the duration of ice and from year to year. Okay, So, so that's all the recovery data and all the visual pictures. Now to get more into what's going on physiologically. And if you can remember the butter and the oil picture that I showed, if you think of butter as saturated and oil as more unsaturated, it'll help you kind of understand. I know there's a lot up here on this table, but I'll try to kind of pick apart what we need. So it's just 2014 and 2015, and there are different types of fatty acids listed across. And there's saturated fatty acids over here, and then unsaturated fatty acids here, and then the same for on the other side for 2015. And this is just so the amount or percent of each of those fatty acids within the crown tissue of plants that were treated with one of our treatments. And so if you look at keep the untreated kind of in the back of your mind down here, and you compare that to some of our treatments, you see that for untreated, we had a higher amount of saturated fatty acids, whereas some of our treatments like Civitas, propiconazole, and methfluidide had less saturated fatty acids. And these were very consistent for both years. And so if you remember, the saturated was more like butter and therefore was rigid. Things get rigid in the wintertime, right? So anything the plant can do that can reduce that rigidity is helpful to the plant. So the fact that these treatments seem to have less saturated fatty acids or maybe less rigidity could help the cell membranes in those crown tissues overwinter or survive dormancy. Same with, and consistent with that, if we see a change in saturated fatty acids, we kind of expect to see, the opposite change in unsaturated fatty acids because they're, reverting between each other. They're kind of shifting, back and forth between saturated and unsaturated, depending on the temperature outside and what the plant needs. So again, look down here at the untreated plants. They had a lower amount of unsaturated fatty acids than those that were treated with some of our treatments, Civitas, propiconazole, and methfluidide. And so that says that, these treated plants that were treated with these compounds could be more fluid under winter conditions compared to those that had maybe less unsaturated fatty acids. So I put that back to refresh your memory, but I think I explained it pretty good in the table. So, the treated plants are able to kind of maintain their membranes more like oil or more in a less rigid state under ice or low temperature conditions compared to those that were not treated. And so another interesting thing that we kind of, we can actually weed out, other than the fact that there's just these saturated or unsaturated difference, there are some of these fatty acids are actually important for other metabolic purposes. So not just in the membrane, but they can also be in the membrane. But so they're involved in other pathways in the plant. And so an example is linoleic acid is actually a precursor to jasmonic acid. And that's involved in stress responses. It's involved in response to wounding. So every time you mow your grass, there's this spike in jasmonic acid that helps the plant heal that wound, essentially. And that happens amazingly quickly in grasses, especially, some of the grasses that we grow for turf. And so I have a lot of other research going on looking at hormone responses and things like that. So this is of particular interest to me, and I think it's also of interest to IntelliGrow, and it can provide a possible reason, in addition to just there's this change in fatty acids. It could provide another possible reason of why Civitas could have been the top performer in the study, because Civitas also, as I mentioned earlier in the beginning, just briefly, is involved in the ISR pathway, or this induced systemic resistance pathway, which, so not only is jasmonic acid involved in wounding response, it's also response to pathogens. So any perhaps bacteria or fungal pathogens that can, affect the plant. Jasmolic acid helps in kind of combating that or signaling the plant to combat that. So just kind of an interesting thing, and maybe a future avenue of research for us. And so I generally kind of said my conclusions within my slides, but just to recap, the conclusions that we can really draw from our fall field work with this study is that, essentially we think that, you can use these PGR treatments for winter protection and really not sacrifice the turf quality in the fall. And then similar in the field, in both years, we didn't get, consistent ice cover, so we can't really, make comments on the ice cover in the winter. But for PGRs, there was not really too much negative effect on spring green up, with the exception of the fluoride. It kind of, if you remember from the figure, it kind of delayed that spring green up slightly, like by a few weeks, but it eventually caught up to the other field plots as well. So can't really say too specifically that any negative thing was happening there. So, for our other conclusions related to the ice specifically or low temperature conditions, these PGRs seem to be, a viable option for turf managers. Trinexapac ethyl, we kind of picked that one out because if you remember back to my survey results, that's the one that everybody was using, and that's the one that we know, everybody uses a lot. And there was some kind of anecdotal evidence or people saying, hearsay, that Trinexapac ethyl was damaging plots due to winter. From our results, it is possible. From our results, we didn't get statistical differences. There was these visual differences. At least when you quantify things, the bars on the graph would look lower all the time for Trinexapac ethyl, but they weren't statistically different. So we can't say that Primo, did any negative effects to the plots. And then Civitas, fluoride, propiconazole, improved regrowth from ice conditions, and to some extent also improved regrowth after low temperature conditions without ice. So so we need we need more research to maybe better target rates and frequencies of these treatments, and perhaps seeing whether this is true under fairway conditions, maybe longer heights of cut, or maybe under field conditions that can more closely represent what you guys would do out in the field. But we would need some place where we could maintain ice to a more consistent level. So but yeah, so that's all I have. I hope you enjoy the presentation. We have a lot of people working on this in my lab. The main student that works on it is Kevin Laskowski, my graduate student. He is now doing his PhD in my lab. This is his PhD work, actually, the winter kill. He did his master's in my lab as well on drought and traffic research. And then Kevin Frank for kind of the extension part of this with the survey and everything. And then financial support came from Michigan Turfgrass Foundation, Syngenta, IntelliGrow, USGA, Project Green of MSU, and the Ag Bio Research of MSU. So very thankful for all the financial support of this project.
Thanks, Emily. A lot of great information there. We do have a question. And those of you who might have additional questions, please raise your hand and we'll unmute you, or type it in the question answer box. Is it possible that the ester oil-based product can absorb heat in the spring and lead to faster regrowth? We've seen this as a benefit in the spring, but a detriment in the summer. I was just curious if it was impacting growth in spring conditions.
So, I mean, I think they're referring to the Civitas, like the oil-based product. We did see that increase in the spring in terms of regrowth. Because we saw it in and the field as well. We know our results were consistent. we don't know whether it's any result of temperature. It certainly could be. This was a very kind of mostly applied study other than the fatty acids to see, okay, does this work? Not really not trying to define every single possibility that could have caused the improvement due to the treatment. But, we certainly could measure that. We could measure, use an infrared gun and measure the temperature of the canopy at given times to see whether it was different. I don't know if that would be, if it would be significant to see maybe a couple degrees, maybe like a point degree higher if you could kind of, if you had devices that were accurate enough to kind of read that out. So I don't know how much, change in temperature you would really see due to a treatment like that. So I guess my real answer is I don't know, and perhaps it's something we can look at.
Right, as you said, more research needed. I thank everybody for joining us today. IntelliGrow has sponsored this event through our external education program, and so you'll want to use the approval code 999-183-2325010 when you go to the website to enter for your education points. Anybody who's listening to the recording in the future, make sure you use the date that you're watching rather than the original date of presentation for that. There's another question. What formula of Civitas was used?
At the time, it was called Civitas 1, and I was told that is now Civitas Turfgrass Defense. So if you contact someone at IntelliGrow, they probably know way more about the formulation than I do. That's really all the information that I have.
Okay, great, thank you. I do want to mention that the Environmental Leaders of Golf Awards are open right now. If you're interested in applications are due before the 30th of September, and so we welcome you to submit those, anyone who is interested. You can find more information on the website, Environmental Leaders of Golf, sponsored by Golf Digest, GCSA, through the Environmental Institute. Not seeing any other questions. Emily, did you have any other closing remarks for us today?
No, I just like to thank everybody thanks for inviting me to give this seminar, and thanks for attending.
Absolutely. We appreciate your time and energy in presenting. Those of you who joined us, we appreciate that as well. Hope to see you online again soon. Have a great day, everybody.
You too. Bye.